Ladies and gentlemen, welcome to Portland's 1991-92 Science, Technology, and Society Lectures. My name is Terry Bristol, and I'm the President and Executive Director of the Institute for Science, Engineering, and Public Policy. It's abbreviated ICEP, and it's ICEP that organizes this lecture series. I'd like to take a moment to thank the co-sponsors of the series, Precision Cast Parts Corporation, the engineering firm of CH2M Hill, the high-tech PR firm Wagner Edstrom, Oregon Episcopal School, IEEE, which is the Professional Society of Electrical and Electronic Engineers, and the stalwarts who helped us get this off the ground, Oregon Public Broadcasting and Portland State University. I'd also like to thank the Heathman Hotel for providing all our speakers with first-class accommodation while they're in Portland. And those of you who have patron tickets and are going to the reception, that's in the Heathman, and you can connect on the mezzanine level. You don't even have to go outside. It's right over there. I wanted to mention, I don't know how many of you saw this. I don't know how well you can see it from there without the lights, but this is a poster we did for this. We did posters in the past, and you probably, if you're a regular, you've seen them. Jane Goodall poster we did won a couple of national awards. Anyway, we're back into doing posters, and the reason we're back into doing posters, which turned out to be rather expensive as it goes, is because Wagner Edstrom, which is one of our underwriters, has expanded his creative department, and they hired this fabulous guy by the name of Gordon Bowen, who has agreed to do these posters for us, and it doesn't cost us anything. And so I want to say thank you to Wagner Edstrom for that. These are really nice. We made a very early commitment in this project to really have the arts as part of what we were doing, and so this gets us back up to speed on it, and really appreciate it. I want to acknowledge the very important role in the creation of the series played by the science teachers in the Portland Public Schools, who've also been an ongoing source of support and encouragement. Indeed, the study guide, which we have for this series, was conceived by the science teachers and funded in part by a grant from the Curriculum Development Department of Portland Public Schools. If you're a seasoned subscriber, you got one automatically. You might have bought one out there. This is for the first three speakers, so it includes Paul Davies in this. If you want to get one, I think they're a minimal price for them out there. And there will be another one for the three people, Prigogine, Polkinghorn, and it's on the back of your program, and Margulis. In the spring, there'll be another study guide that'll be available early in February. Okay. I wanted to single out two people at Portland Public Schools, particularly Steve Carlson, who's the science specialist for Portland Public Schools, who has been with me from the beginning on this, and the real guy that makes things happen, and Shirley Glick, who's the director of Curriculum Development at Portland Public Schools, who's really got behind us on this and other projects which will emerge down the line. As part of our relationship with Portland Public Schools this year, I want to mention Dr. Davies spent half a day Wednesday at Wilson High School with about 600 students and teachers from both Wilson, and they brought a group over from Metropolitan Learning Center where he gave a little over an hour talk on black holes, wormholes, and time travel. And then these kids grilled him for about 45 minutes on top of that. So that's one of the really nice spin-offs that we've managed to develop out of this series, is having these people be here for 3 or 4 days and go around to some of the schools and do a few extra things. And I don't have one. Anyway, there's some papers stuck into your programs, and one of them says question on it, and it also has a place for your name for if you want to be on our mailing list. And if you're on the mailing list, then you will not miss any of these things. You'll get a direct mail notice when we do something in particular. Now, we also have, I played this little game, and we came up with some goodies this time, which is to encourage, some people can't get the pen out of their pocket and write their name down. So we make a little game out of it, which is, and we got lucky here. Paul Davies has 2 new books coming out, and as luck would have it, we don't have either of them here. However, he and I called up Simon & Schuster, particularly when he called up Simon & Schuster yesterday and sort of said, why aren't these books here? And they're actually not published, but I have here The Matter Myth, which is the next book. There's actually two books that are almost coming out simultaneously in The Matter Myth, and these are the galleys. And only about 20 or 30 of these exist in the world. And we happen to have 6 of them, which they sent to us. So we're going to have him autograph them. And for those of you who put your name on the little piece of paper and drop it to the ushers at the end, we will have a little drawing, and we will send you one of these books. They will probably be worth millions of dollars. I mean, limited edition. There'll be no more of these made. So 6 of those, The Matter Myth, and then miraculously, I mean, we talked to all the key people at Simon & Schuster. You got to have this book here. This can't be done. It won't be available. It's not going to be printed till December 6th. It won't be, back from the warehouse till the 30th. And Paul called his key guy there. He said, you got to talk to this one guy. So he talks to the guy, and the guy says, magically, there are some books on my table right now, and this is The Mind of God, which is the one we all wanted to read, and we have 3 copies of that, which they got to us. Anyway, so that's all we have, unfortunately. But so we are throwing those into the pot too. So as we stir up the thing and draw out things, there are 3 autographed copies of The Mind of God to be given to whoever turns those in too. And this will be. Oh, now the other thing is with both. Well, not entirely sure. With The Mind of God, you can order the book out there, and they say that they'll have it to you by Christmas if you want it. So they'll deliver it to you. If you want to just give us an order out there, we'll pass it on to Simon & Schuster. Simon & Schuster will send it to you by then. So any of you who want a great Christmas present, Mind of God for Christmas? Yes. Okay. And I'm not sure about The Matter Myth. I did not get it from the horse's mouth that this has actually been printed yet. These are just galleys. So if they can't get it to you by Christmas, it'll be soon after that if you want to get that too. All right, so that's that. Yes? Oh, and on the question thing, at the end of the lecture, if you want to write a question, you can write it now. And between end of lecture and beginning of Q&A, the ushers will come down, and those of you who want to ask questions by writing them out rather than standing at the microphones or something, we're going to do that this time. And so I'll collect them down there and kind of sort through and sort out the duplicates and stuff and feed them to Paul. So he'll take some live questions and some that way too. And those will be, of course, put in. If you put your name on those will be put in for the drawing as well. Got through all that, right? Guess who finally gave us some dates? If you've looked inside your program, you already know. Stephen Hawking, who I stuck my neck out in the summer and at the first lecture and said, guess what, Stephen Hawking's probably coming. And then it just stalled out, and he broke his arm, he got hit by a taxi cab. I mean, it was... Anyway, he recovered very quickly from that, apparently. And Stephen is, of course, the author of the A Brief History of Time, physicist at Cambridge, one of the early developers of theory of black holes. So he's coming. He'll be here. I just heard this, like they faxed me this on November 25th and said, how would you like January 25th? I said, you mean like 1992? And they said, yes. So we're going to do it. Never to be daunted. So he'll be here, same place right here, on January 24th. That's a Friday. And he'll also be in Eugene doing the same program Saturday night, January 25th. For those of you who are wondering, what he does, he writes up his lecture ahead of time, and each one's unique, and he taps it into his computer, and then he'll come out here with his little go-kart, and he has a voice simulator on his computer, and he will trigger the slides, and he will give a talk right here. And then there will also be a question and answer period, and since it takes him like about 10 minutes to tap in and answer, and that gets a little trying, what we're going to do is have people submit questions ahead of time, and then we'll kind of read the questions, and then they'll kind of press the button and give the answer or whatever. That's roughly how I understand what's going to go on. Now, the tickets go on sale for this in Portland tomorrow morning. We got that really moving. And in Eugene through the Holt Center middle of next week. It's in the info in your program. I'm close to the end here, folks. Thanks. In recognition of the support for the series, we're holding a special block of prime tickets for purchase by our season subscribers, of course, and members of ICEP. So if you call up Fast Ticks or the Holt and say, I'm a season subscriber, and give me your name, we are going to take a bunch of the best seats and for a couple of weeks hold those out, the Stephen Hawking thing, to just say thanks for you people who bought season tickets and supported us. Okay. Oh, we're also just, And again, thanks to Portland Public Schools, we're going to do something Friday afternoon, which will be just for school children with Stephen Hawking. So like about 1 or 2 in the afternoon, all the kids are going to come down here and do a little special program just for them with Stephen Hawking. And that's just, if you have a kid that wants to come to that, have them ask through their school, and they'll find a way to get to it. Close. Before I introduce our introducer, I want to congratulate Oregon Public Broadcasting on their a very recent significant national award they received last night, in fact, in Washington, D.C., for To the Last Fish, which is OPB's frontline television documentary about the depletion of ocean fish populations. This won the Golden Eagle Award of the Council on International Non-Theatrical Events. The program earned top honors in the Protection Ecology category. Congratulations, OPB, for your work, which helps to monitor such critical environmental issues. Keep it up. Yes. I'll collect my things here. And without further ado, it's my pleasure to introduce Maynard Orme, who's the president and CEO of Oregon Public Broadcasting, who will introduce Dr. Paul Davies.
Thank you, Terry. Excuse me. Thank you, Terry, for those nice words. Good evening to you all, and welcome to tonight's ISEP lecture. I'm always struck every time I appear here how marvelous it is to hear through the ISEP lecture series these brilliant thinkers peeling off layers of ignorance like onion skins to get closer through the development of knowledge to wisdom and truth. And consequently tonight it's a special pleasure to introduce to you one of the world's premier scientific writers. Born in England on April 22nd, 1946, Paul Davies is professor of mathematical physics at the University of Adelaide in Australia. From 1980 to 90, he was professor of theoretical physics at the University of Newcastle upon the Tyne, where he also was head of the department. Dr. Davies received his Bachelor of Science in Physics from University College London in 1967 and his PhD in theoretical physics from the University College London in 1970. Dr. Davies began his career in atomic astrophysics, but soon moved into particle physics and cosmology. Most of his writing has been in the area of quantum field theory in curved space-time. He has discovered and investigated a number of quantum effects associated with black holes and the very early stages of the Big Bang. He has also helped develop the thermodynamic theory of black holes. Among other research, he is interested in the nature of time and its relation to the evolution of the universe. In recent years, he has broadened the research to include chaotic and self-organizing systems and the relationship between physics and biology. Davies is considered by many to be one of the most adept science writers on either side of the Atlantic, including critics from both New York Times and the Washington Post. He entertains, challenges, and perplexes his readers with fascinating excursions into the chaotic realm of the new physics. Drawing on discoveries in the fields of medical research, biological evolution, computers, and astrophysics, Davies says that all matter and energy have the ability to self-organize according to common holistic principles. He rejects the idea of a universe at the mercy of random forces as he addresses the most profound and age-old questions of existence. Questions I'm sure you've asked yourselves. How did the universe begin and how will it end? What is matter? What is mind and can it survive death? What are time and space and how do these relate to ideas about God? Is the order of the universe the result of accident or design? Davies writes that the discoveries of 20th century physics, relativity, and quantum theory are now shaping new ways to explain humankind and its place in the universe. In fact, we may be very close to discovering a unified description of all creation. The new physics, according to Davies, not only suggests but demands a radical redefining of the most fundamental aspects of reality. This reformulated approach is more in accord with mysticism than physical materialism and offers perhaps an even more direct path to God than does religion. His widely popular books, including Other Worlds, God and the New Physics, and Superforce, are appreciated by scholars and lay readers alike. They are consistently praised by critics and reviewers as lucid, witty, elegant, astounding, and even mind-boggling. So, prepare yourself for a provocative and intellectual journey tonight into the fascinating world of the new physics. Ladies and gentlemen, please join me in a warm Oregon welcome for Dr. Paul Davies.
like the picture? Let me tell you about a Jewish man who fell on hard times. His wife had left him, his business had gone broke, and to cap it all, he just dropped his buttered toast onto the carpet. Anyway, looking down gloomily, he suddenly noticed with surprise that the toast had fallen with the buttered side uppermost. Could this mean his luck was changing? He stooped down and gingerly picked up the toast, and he got a plastic bag and put the toast in the plastic bag, and he hurried off to see the rabbi. He said to the rabbi, "Father, tell me, could it be that my luck is changing?" And the rabbi looked somewhat skeptically at the toast, looked at the top, looked at the bottom. Then he took out a magnifying glass, inspected it very carefully, and he turned to a huge stack of books on Jewish law. And he said, "Come back, my son, next week and I'll give you the answer." So the man came back anxiously a week later, and he said to the rabbi, tell me, Father, is it true that my luck has changed?" "No," said the rabbi, shaking his head gravely. "You buttered the wrong side, that's all." The moral of that story is that human beings have a natural desire to look for deep significance in the things that go on around them. And in this search for meaning in the universe, we divide up into two categories, the optimists and the pessimists. Now, if there was a prize for pessimism, it must surely go to a certain Hermann von Helmholtz, a physicist who, in the year 1854, made what is probably the most gloomy pronouncement of any scientific statement ever made. According to Helmholtz, the entire universe is actually doomed. In fact, not only doomed, but in the process of dying. This surely must be the gloomiest thing that has ever been said, because Helmholtz was not just referring to the Earth, he wasn't just saying the Earth is doomed, or the Sun, but the entire cosmos. So I start the presentation this evening with the concept of the dying universe. It gets better from here on. Helmholtz didn't arrive at this conclusion on the basis of any examination of toast, or indeed even by consulting his local minister of religion. He came to the conclusion on the basis of a scientific argument, in fact a very solid scientific argument, which goes under the name of the second law of thermodynamics. You might say, well, what's the first law of thermodynamics? We don't need to get into that. It's the second law that is the key. Now, many people may have heard of the second law of thermodynamics. Let me just take a little while to explain to those of you who haven't what it is about. If you go to the great book of nature and open it at page 3 or somewhere, you will find the second law discussed. And it's a very believable law. Basically, it tells us that things have a natural tendency to crack up, to break down, and to go wrong. And it's not entirely the fault of the politicians. It is actually a basic law of mechanics, or thermodynamics. And here's an example. We know that if you have a machine, it doesn't run itself. There's no such thing as a perpetuum mobile, that every machine needs some fuel to make it run, and it also needs a bit of tender loving care. You can't just abuse it and expect it to perform properly. Perhaps a good example of the second law of thermodynamics at work is our old friend Humpty Dumpty. This is what physicists call a disordering transition. Humpty clearly succeeded in disordering himself rather badly when falling off a wall, and even with the attention of all the king's horses and men, it was impossible to reassemble him. So we call this an irreversible process, and it's a good example of how in nature well-ordered things can so easily become disordered, but it's much harder to go back the other way. It will be much harder to put Humpty to get together again than to break him in the first place. So I think we're all very familiar with this law. The key to understanding Helmholtz's statement is that the law doesn't just apply to Humpty Dumpty and machines, it applies to the universe as a whole. And in its cosmic context, we might say that every day the universe becomes more and more chaotic. The total amount of chaos, or entropy, as it's known in the trade, is going up the whole time, and this bestows upon the universe what we call an arrow of time. That is, it introduces a distinction between the past and the future, so that if I should take a movie film of some sequence of events, for example, like Humpty falling off the wall, and play the movie film backwards, you would all spot the deception. We can all tell basically which way time flows. And the indicator of this unidirectional change is this rise in entropy. Entropy is just a technical term for chaos, so you needn't worry too much about that. Now, let's get a little bit more specific. Why is it that the universe as a whole is engaged in this one-way rise in entropy? What are the main processes that actually bring that about? This is supposed to be a picture of a typical region of the universe, and it, of course, consists of hot stars inhabiting dark, cold, largely empty space. And this is a condition of thermodynamic disequilibrium, because the stars are hot and the space is cold, and this means that heat flows out of the stars off into space and it doesn't return. It's an irreversible process. And the flow of heat from hot to cold is a very good example of the second law of thermodynamics at work, because it represents a rise in entropy. The arrangement of the energy is more ordered if it's all locked up in the stars than when it's spread out all around the universe. And so this general emission of radiation from the hot stars into the empty space is a good example of the universe running down, for the simple reason that those stars need fuel, just like the machine I showed. They need fuel to keep burning, and eventually they'll run out of fuel and burn out. So this is the basic reason behind Helmholtz's statement that the entire universe is on this one-way slide to a state of thermodynamic equilibrium, which became known as the heat death of the universe. That was the popular term, the heat death of the universe. In a way, it's not so much a death by heat, it's more like a death by boredom, because what it's predicting is that all of the interesting activity, all of the variety and diversity of physical systems and forms are slowly, steadily, and inexorably degenerating towards some final state of total equilibrium in which the energy that's available is shared out equally among all possible systems in a way that means that no further interesting things can happen. And that was the basis of this terrible 19th century prediction that the universe is doomed. It's in the process of dying, the heat death, slow, painful, and inexorable. It is, as it were, slowly choking on its own entropy as it slides towards this end state. I suppose that this must be the ultimate ecological crisis. The entire universe is evidently stuck with this. Now, the prediction of a heat death of the universe has exercised a tremendous influence on several generations of scientists and philosophers. It isn't just one of these scientific pronouncements that gets published somewhere in a journal and maybe picked up by a newspaper and that's it, nobody pays any attention. This one really did grab the attention of all the important thinkers in the 19th century, including a certain Bertrand Russell. And after contemplating the implications of the second law of thermodynamics, Russell wrote the following words in his book, Why I Am Not a Christian. And I'll put them up and I'll read them out to you for those at the back who can't see that. So this is what Russell wrote. All the labors of the ages, all the devotion, all the inspiration, all the noonday brightness of human genius are destined to extinction in the vast death of the solar system. And the whole temple of man's achievement must inevitably be buried beneath the debris of a universe in ruins. All these things, if not quite beyond dispute, are yet so nearly certain that no philosophy which rejects them can hope to stand. Only within the scaffolding of these truths, only on the firm foundation of unyielding despair, can the soul's habitation henceforth be safely built. Well, it might have been a bad day for Russell. Perhaps he dropped his toast. But he was obviously deeply moved by the implications of this second law of thermodynamics. Now, I've said this was several generations. Russell, of course, wrote those words a long time ago, about the turn of the century, but in 1974 we can read the following from Jacques Monod's book, famous book, Chance and Necessity. Man at last knows that he is alone in the unfeeling immensity of the universe, out of which he emerged only by chance. And then, slightly more recently, Stephen Weinberg, the more the universe seems comprehensible, the more it also seems pointless. The effort to understand the universe is one of the very few things that lifts human life a little above the level of farce and gives it some of the grace of tragedy. Well, so much for that. Now for the good news. Misconception number one, the universe is dying. What I want to argue this evening is that, although in a technical sense the second law of thermodynamics must be correct, when it comes to evaluating its cosmological implications, I think it's given a grossly misleading picture as to the true indicator of cosmic change. And I'd like to share with you a different vision of the universe, one that's based upon my own research in the last 10 or 15 years, and also the research of many of my colleagues who are beginning to see not only the universe as a whole, but the processes of nature in a totally different way. So let me start right back at the beginning. And of course, in cosmology, the beginning is the famous Big Bang. It's a little difficult to read. At the top there it says, time began 18 billion years ago. That's an important point, incidentally. I don't want to get too much into this. We believe that the Big Bang was not just the beginning of matter and energy and all of the interesting activity, but it was the beginning of space and time itself. In other words, don't ask me at the end of this lecture what happened before the Big Bang, because I'll tell you the answer. There was no before. It's a meaningless question. Time itself began with the Big Bang. Now, we have good evidence that there really was a Big Bang, and in the last few years we've been able to build up a pretty good picture of what happened at the beginning. And it really wasn't like that. There was nobody actually around at the time, of course, to photograph it. So that's an artist's impression of the Big Bang. It's actually me who drew that. So it leaves a bit to be desired, and it didn't reproduce too well there. But I'm now going to show you a much more accurate picture of the very first moment after the beginning of the Big Bang, and here it is. It's important to realize it's not to scale. It's actually a lot smaller than that. There's a serious point about that, which is that the whole point is, from what we know about the early universe, it was almost totally featureless, and in fact many people now believe that the universe began with essentially empty space, that there was just nothing there, and that all of what we see now, all of the good things, and all of the bad things too, have emerged from this featureless origin. A lot of people talk about the Big Bang as the creation. You can see books and articles written on that sort of theme. The Big Bang was the creation of the universe. But what I should be showing you is that this is really not the way it happened. That it's true the Big Bang was the origin of space, the first little glimmer of space and time, but in no sense was it the creation of everything that is important in the universe. It is not the case, as people believed maybe 100 years ago, that somehow an imprint of all of the richness and variety of forms that exist in the universe today was already present in the Big Bang. It's not that the universe is somehow working its way from some, or unfolding from some already existing structure. What we shall see is that the development of the universe as it expands and ages is more like one of continuing creativity. And this is represented in this next picture here, that we start out down the bottom there, you see, well, we don't know what. I could have been lecturing on a different topic. I could have been lecturing on how the universe can come to exist from nothing at all. But Stephen Hawking will do that when he comes here in January. I'm sure that will be the topic he will lecture on. And so we know ways in which you can get universes from nothing. So let's assume that that can happen, and that we start out with essentially just a blob of empty space. And now we think of the universe today with the enormous variety of different complicated things, the richness of structure that we have. Not just living systems, but non-living systems too. Immense complexity. And it's all arisen from this initially featureless state. So the story of the universe is not really, as Helmholtz would have us believe, it's not really the story of something that started out perfect, imprinted with the Creator's perfect hand, and then has degenerated towards, or is sliding towards some state of total degeneration. It's really a story that goes like this. It's a story of simplicity developing or unfolding towards complexity. That the initial state of the universe was a very simple state, and the state we now have is a much more complicated one. So it's the emergence of complexity that is the key indicator of cosmic change. I like to talk about organization and distinguish it from order. And this is a subtlety, and I'll try and bring out this subtlety as I go on. As we shall see, the complexity of the universe isn't just any old complexity. It's not just complication. It's complexity of a very interesting and subtle kind, which I think is best captured by the word organization. It's organized complexity. Clearly, the most obvious examples of organized complexity are living organisms, like human beings, highly organized complexity. And these things, this organization, this complex organization, has emerged since the beginning from that simple origin. But at the same time, we cannot ignore the second law of thermodynamics. Helmholtz wasn't wrong to say that it applied to the universe. He was simply wrong in concluding, or other people in fact concluded, that this meant that everything is just sort of inevitably sliding downwards rather than advancing. What we actually have is two arrows of time. One which we might, I suppose, call the optimistic arrow. That's the one on the... That's a trick laser pointer there. It's pointing at me. I knew it was a trick lock. So there we go. I'll be coming on to lasers in a moment. So there we have the optimistic arrow. That's the advance of cosmic organization, starting out with next to nothing and developing into all the good things we see today. And then alongside this arrow is this pessimistic or degenerative arrow, representing the rise of entropy, or alternatively the decline of order. And so I'm distinguishing order and organization. It's a subtle distinction, but I hope it will become apparent that there's a real distinction as we go on. But just for now, the point I want to make is that we should really see the development of the universe as two different sorts of change taking place. These two types of change taking place side by side, they're not actually directly opposed to each other in the letter of the law, but in the spirit of the law they are. That the growth of organization sort of looks as though it's going against the growth of entropy, but it's not, as we shall see, that they are actually reconcilable, these two things. So what we can really see is, I suppose, a sort of tussle taking place between these two opposing tendencies. And I'm reminded of the gods of Hindu philosophy. Now, I've got to get this right the right way. It's a little bit like Brahma, the creator, and Shiva, the destroyer. I think I've got that wrong. It's a bit clever, this, when you have to start superimposing these things. So it's sort of reminiscent of that. And I think, in fact, most cultures have their stories about creation and destruction as opposing tendencies. And it's really only been in this last 100 years where culture, or at least Western culture, has been so dominated by scientific thinking that we've got away from this idea of balanced or opposing tendencies, and that there has been this story of only unidirectional change, and this unidirectional change being for the worse, this degeneration. But most cultures are quite comfortable with the idea of these opposing tendencies. So this is just summarizing the point that the universe started, so to speak, with a blank canvas. I like this image of God the Creator not sort of making a universe in one go, but a blank canvas to be filled in step by step as it unfolds. That's just a metaphor, but I think it's a nice one. And the essence is that the creative power of the universe is something that continues for all time. When we talk about, or people talk about the creation as something over and done with, as though the creative ability of nature is something that could have only happened once to have brought the universe into being, that's missing the main point of the story, I think, which is that nature has never ceased to be creative, and that as the universe expands and develops, this creativity simply continues. And most of what we see in the universe has actually come since the beginning. Karl Popper has actually emphasized the importance, he calls it the greatest riddle of cosmology there, the importance of this creative power in nature. And the fact that matter and energy seem to have some uncanny innate ability to be able to bring about these self-organizing processes. We'll see in a few moments with some examples how it is that human beings don't have to impose this creativity on matter and energy themselves. It's something that matter and energy simply have. They have it as an innate ability, an innate creativity, able to bring forth new and more complex systems. So we see a sort of logical as well as time dependence in which, sitting at the bottom of this great scheme, we have down here the laws of physics. For those that can't see too well, we start out with the laws of physics, you see, and we believe that given those laws of physics, space-time can come into existence as a result of quantum processes. So we can leap from the laws of physics to this rudimentary space-time, but there's nothing much in it, you see. It's more or less structureless, featureless. And from space-time, matter emerges due to further physical processes, and these are physical processes that occur after the Big Bang. It's important to realize that the Big Bang itself didn't give us matter. The matter was created just a little bit afterwards, only a tiny fraction of a second afterwards, but it was later. But this matter was entirely formless. Say 1 second after the Big Bang, as far as we know, the universe just consisted of a soup of subatomic particles uniformly distributed throughout the universe at a more or less uniform temperature. And it's a very boring state of affairs. It was essentially a state of thermodynamic equilibrium. Not a very exciting universe, not a very promising universe. Had you been around at the time, you would have thought, well, this isn't much fun. This isn't going to turn out to be very much. And who would have guessed? Who would have guessed on the basis of just seeing all that stuff there smeared around in the universe and knowing the laws of physics, who would have guessed that those laws could trigger this long, complicated sequence of changes which have progressively organized this matter into the enormously rich and diverse variety of physical forms and systems that we see adorning the universe today. We live in a universe that is absolutely full of elaborate activity and organized systems. Wherever we look, from the smallest scale of size right out to the most distant and far-flung galaxies, we see this marvelously intricate elaboration of matter and energy. And none of that was present at the beginning. And then, of course, at the top of this, finally, matter organizes itself sufficiently so that we can regard it as being living, that we get biological systems, and ultimately living systems have developed so that consciousness has emerged in the universe, and then we get observers, individuals who can reflect and look back on this chain of logical dependence here and wonder what it all means for them. The best description that I have for this view of the universe, in which we start out with essentially nothing and the elaboration develops of its own accord without any need for, as it were, outside interference, is the self-organizing universe. The self-organizing universe. It's actually the title of a book by Eric Jantsch some years ago, and I think it's a very inspiring way of looking at the processes of nature. what a long way we've come since the time of Helmholtz, in which the image was of the self-destroying universe. We now live with the self-organizing universe, in which we recognize that even stupid clod-like particles of matter can, under some circumstances, do the most amazing things. Now, I've been talking in generalities. Let me give you some specific examples of how stupid matter can do amazing things. Let me give you a very homely example that you can see without traveling very far from your own kitchen. Imagine that you've got a pan of liquid, this could be water, for example, which you place on the stove, and you heat it from below. Now, if you heat a fluid from below, first of all, nothing very much happens. If you were to peer into the top, you wouldn't see very much going on at first. It would just look like a featureless uniform fluid, a little bit like the universe in its early stages. But the effect of heating it from below eventually causes something remarkable to happen. It causes a pattern of convection to occur. The hot liquid at the bottom, as it gets hotter, it gets less dense and it wants to rise, and the cold liquid at the top is more dense and that would like to fall, and eventually they have to sort of change places, so to speak. And that occurs when the fluid starts to move, the hot fluid rises and the cold fluid falls, but it doesn't do it in any old way. It does it in a rather special way. It forms a pattern of convective flow. And if you do this experiment very carefully, you don't notice it in the kitchen, but if you do it in a laboratory and do it very carefully, what you find is that that convective pattern organizes itself into a most extraordinary system of cells that look like this. Is a photograph. It looks a bit like a honeycomb, a system of hexagonal cells. You see how precisely they're arranged? This one is a slightly more complicated arrangement, but you can get the picture, I'm sure. But the essential thing is that the featureless fluid, when it's driven away from equilibrium by the effect of heating it from beneath, organizes itself. It's not the experimenter who imposes these hexagonal cells, it's the system itself that finds this pattern and creates this pattern. And if you were to ask in advance where exactly would one of these hexagonal cells be, it would be impossible to know, because what actually happens is that as the fluid is driven more and more from equilibrium, it spontaneously leaps into this new, more highly organized state. And the effect of the most minute fluctuations on the system can affect the actual layout of the pattern at the end. And so it's a system which is essentially unpredictable in its details. It is therefore, in some sense, genuinely spontaneous, and yet what it does is to go from a featureless beginning and searches and finds this more elaborate, more highly organized state afterwards. And it does it entirely on its own. It is a self-organizing system. It's not something we do to it. That's the important point. Now, the astonishing thing is this. You see, many people who work in the theory of fluids or do experiments of these sorts don't find anything too astounding about this. But you have to stop and think what's going on here, because in there, each molecule of water is simply pushed and pulled blindly by its neighbors. It can't reach out across the whole body of the liquid and know what's going on over here, for example. The forces that act between these molecules are very short in range. They're just immediate neighbor forces. And so it's all the more astonishing then that these trillions and trillions of molecules can somehow get together and cooperate and organize themselves into these large-scale patterns, given that every molecule is just a stupid molecule. I mean, it doesn't have a plan, there's no conspiracy, it doesn't get together with the other molecules saying, well, let's all move over this way because they're all moving over that way. It's entirely blind. These are blind and purposeless forces, and yet they are behaving in a manner as if the whole thing had been somehow designed in advance. So we see that even just stupid water molecules can nevertheless do these amazing things. Let me give you another example. You've all heard of the laser, and I'm holding one in my hand. The laser is a good example of a self-organizing system. If you take light from an ordinary lamp, like one of these spotlights up here, it just consists of a whole jumble of different light waves all mixed up together. That's like this. Lots of little wavelets all superimposed in a complicated mess. The key thing about a laser, and that's why the quality of the light is so interesting and so useful, is that all those little waves are actually in step with each other, that they've organized themselves to form this coherent beam of very pure undulation. The electromagnetic wave, the light wave, has got this pure waveform. And that's the important point about the laser. Now, the thing is that the manufacturer of the laser doesn't impose that waveform on it. It's not that somebody has designed this, as it were, manipulated it to put that waveform in advance. The laser does it for itself. All the manufacturer has to do is to drive that system, in this case it will be gas, to drive it very far from equilibrium, and when it reaches, I mean, I won't go into technical details, but the point is it reaches some critical threshold at which suddenly all that jumbled light of that sort suddenly flips over and becomes this highly organized waveform. So it's a spontaneous, self-organizing process. And it's the sort of thing you probably wouldn't have guessed could even happen in advance. You might think that if you just get a lot of atoms together and excite them and then let them emit light, that it will just happen in a sort of random and disorganized manner. But it's interesting that Einstein was actually able to predict the existence of this phenomenon, essentially. I mean, he didn't really think of it this way, but the essence of the idea is already present in Einstein's work from the end of the first 2 decades of this century. So already at that time, the ingredients were there. But this is another good example, I think, of a system which organizes itself and flips into that more highly ordered state when it's driven from equilibrium. There are examples all around us, and I was interested to note that Ilya Prigogine will be coming to talk later in this series. He is probably the person who has most drawn attention of the scientific community to the possibilities of self-organizing processes, and he has the most amazing examples that he's studied, including one which I hope he gets to demonstrate here because it's very striking, where you mix a lot of chemicals together, and normally when you do that a reaction takes place and then you end up with some sort of final state. You might mix a blue liquid and a red liquid and end up with a green liquid or something, I don't know. The sort of things that one remembers from school days in chemistry, and that really is called equilibrium chemistry. That's what happens when you allow chemical reactions to take place close to a state of equilibrium. But what Prigogine has done is to study examples of where chemical processes take place very far from equilibrium, where you keep forcing the reagents through the system, and you keep a flow going the whole time, and you don't let the system settle down to equilibrium. And you might think that under those circumstances you wouldn't see anything especially interesting, that if you're always forcing the thing away from equilibrium. But it turns out with certain mixtures, what happens is truly remarkable. You can get these processes that take place where you look at the fluid and it spontaneously grows interesting shapes, like spiral shapes, and all sorts of arms and things grow out, and it looks very, very intriguing. And these patterns form entirely on their own. It's entirely a self-organizing, spontaneous process. If you do it slightly differently, you can also get these fluids to pulsate. So you get something like a chemical clock, and they pulsate quite rhythmically. You might have blue 1 second and then going to red the next second, then back to blue, and so on. And again, what you're dealing with is countless trillions of molecules that are all in some sense cooperating. It's a little bit like if all the molecules in this room, instead of just rushing around chaotically, banging into each other and banging into the walls, and all doing their own thing, all of a sudden to say, hang on, let's all do this together, and they all march over this way together and bounce off that wall and all back this way and bounce off that wall. It's sort of ridiculous. You think, well, how could you ever make all these molecules do that? But in these chemical mixtures, that's precisely what happens. You get these systems, chemical systems, you drive them far enough from equilibrium, and they all start cooperating, doing this, doing that. And Prigogine will show some of these things, and I think they're very striking indeed. But you don't actually have to set these things up in the laboratory to make it work. So far, what I've been telling you about is really basically laboratory type things, heating fluids, making lasers, mixing chemicals. But what happens if we just look in nature? Do we see examples of self-organization in nature? Well, we sure do, and there's some very pretty pictures of some of these. You'll recognize this. This is Jupiter, the planet Jupiter, and you'll notice that it's not a very good picture, but it serves to make the point that it's covered with these bands of different colors and these sort of vortices and things all over it. And these are very familiar now, these pictures. In the early days, they were a great surprise to astronomers because they didn't really know how these different patterns should come to exist. This is a better better picture, it wasn't terribly clear what physical processes would lead to this type of patterning formation. Well, now we understand that these are also examples of self-organizing processes at work. This behavior of fluids forming these sorts of wiggly patterns here, and in particular forming vortices, a very simple example of how fluids don't necessarily flow uniformly. In this case, I say fluids. This is the atmosphere of Jupiter. This is a whole mix of rather noxious chemicals, and because the planet rotates fast, it's all very violent in here. But you don't just get a complete random mess. What you get when you look carefully is an exquisitely highly orchestrated and organized system of patterns, some of which are very stable. And in particular, the great red spot of Jupiter, which you've probably heard about. Here's a picture of it. This great red spot provides a very good example of a self-organizing, stable system. I don't think anybody made that spot. It's not clear how long it's been there, but probably some hundreds of years. And from what we can tell from computer simulations and things, if someone were to come along with a big axe or something and chop it in two, actually this is about the size of the Earth, so it's bigger than the Earth, I think. So it's not an easy thing to do. But if you imagine, somebody coming along and breaking up that spot, it turns out that it would probably form itself again. So here we have an example of a system that has organized itself into this rather interesting blob-like shape, and that spot just goes around the planet and can be observed with a reasonably modest telescope. Good example of how the gases in the atmosphere of Jupiter have arranged themselves entirely on their own into this shape. Let me give you some other examples. I should say, actually, in passing, because there's another subject that I could have lectured on, but there's no time, which is called chaos. You've probably heard about the new theory of chaos. It turns out that chaotic systems and self-organizing systems are actually very closely related. And that pan of fluid that I was talking about, if you carried on heating it, just made the bottom still hotter, then instead of flowing in that nice regular system of hexagonal cells, the whole thing breaks up and becomes really totally chaotic, and it just sort of boils, and we lose all of that sort of organization. And it turns out that the physical processes which lead to the self-organization, which go under the technical term of nonlinearities, also lead to chaos. And in the example of the great red spot that I was showing, the spot itself could be considered to be a self-organized system, but if you actually follow an element of fluid, it's not, I should emphasize, this spot is not a sort of lump of something that just floats in the atmosphere. It's actually a continuously changing dynamical thing. Gases flow into it and swirl around, and then they come out again and move on. And if you try to model where an element of fluid would actually go and follow it in detail, it turns out that it's chaotic. So here we see self-organization and chaos going hand in hand, and they are actually very, very closely related. And both of these features have the following property, that they're both exquisitely sensitive to the most minute fluctuations, so that for all practical purposes, they're unpredictable. You just don't know in advance that they're going to happen. And that's why I say that if you could have been around in the Big Bang and seen all this boring uniform fluid, you could not have predicted, even with the most powerful computer of the universe, the details of systems in the universe today, like the existence of Jupiter and a spot on its surface. You simply cannot get at that. And so there's this deep link then between chaos and self-organization. Both of them tell us that in some sense the universe, the future of the universe is not already fixed in advance. Now let me give you some further examples of self-organization in the solar system. As we're talking about planets, here's another very striking example. These are the rings of Saturn. I don't want to give you the impression there's anything terribly mysterious about these things I'm showing. I'm not saying we can't explain them, or that there is some sort of mystical force that's organizing them. On the contrary, what I'm saying is that ordinary stupid particles subject to stupid forces can nevertheless display these most magnificent patterns and form them entirely of their own accord. The rings of Saturn form a very good example of what is known in the trade as a fractal structure. If you were to take a section through these rings like this, and plot where the rings are, what you find is that, of course, there are rings and there are gaps, and then you find that in the gaps there are other rings, and in the gaps between those other rings there are other rings, and so on, in a way that has a rather precise scaling relationship. So the rings of Saturn form a good and pleasing example of what is sometimes called a fractal structure. Fractals are very closely associated with chaos, and you've probably seen some of these beautiful pictures that people have published showing different computer-generated fractal shapes that are supposed to illustrate chaotic processes. So these things are all closely tied together. Here's another one, just showing as much as one can on a slide like this, extraordinary level of detail and complexity that is present there. You couldn't know in advance where each of those rings are going to be, even with the most powerful computer in the universe. If you just set a whole lot of little particles going around Saturn and try and work out where the rings will be, work out where some of them are, because they're due to resonances and things, but the general pattern would be entirely beyond you. Let me take another example. Well, this is perhaps the largest scale that we can think about now. I said that the universe began with this more or less uniform distribution of matter and energy, and nothing terribly exciting happening. But of course, as time went on, this fluid eventually arranged itself into a hierarchy of structure, from, on the largest scale, clusters of galaxies, and indeed superclusters of galaxies, down through galaxies themselves, and then stars and planets and clouds and trees and people and so on. So we have this hierarchy of structure. The formation of a galaxy represents one of the largest scales of this self-organizing process. Now, in the beginning, you see, we just had this featureless gas. This is not entirely featureless, but it's sort of a bit of a mess. It's nothing special. It's smeared out. And yet at the end of the day, what you end up with will be something much more like this. What we see here is an example of a galaxy. It's called the Whirlpool Galaxy. And again, the picture doesn't do it justice, but one can actually discern an extraordinary level of complexity and structure and organization there. And the point I want to make is that this Whirlpool Galaxy system is a much more highly organized system in a way that I think can be quantified than that original splodge of gas. And so here we have another example, a cosmological example of self-organization, going from this original cloud of gas down to this, into this amazingly organized structure. Well, all of these examples are taken from sort of out there in the universe to illustrate that nature, on her own, so to speak, can produce these self-organizing processes. But perhaps the most striking example of all that we have of self-organization at work is very close to home indeed, and it's essentially ourselves. It's life itself, representing the most amazing and developed form of self-organization. Because you see, life itself started out in terms of simple molecules, again, stupid, clod-like molecules being pushed and pulled by their neighbors by blind and purposeless forces. No plan existing there, no preordained pattern of unfolding, but nevertheless from these humble beginnings, so we have the enormously rich diversity of life on Earth, and I like to believe life elsewhere in the universe too. So here we see the best example of all of self-organizing systems. Now, all along, I've been telling you that there are two arrows: the optimistic arrow, the growth of organization, and the pessimistic arrow, the growth of entropy. And I've said that these two can coexist. They can, in some sense, both be right, that the entropy can be going up as well as the organization. And you might say, well, how can it be? Doesn't the growth of organization, in some sense, contradict the second law of thermodynamics? The answer is no, it doesn't. And the key to the reconciliation is that self-organizing systems are always open systems. Now, by an open system, I mean one that can exchange matter, energy, and entropy with its environment. Human beings is a very good example. The reason that we don't, well, actually, the human beings is a bad example because most people feel they're getting older, so they are degenerating. But if we think of, say the growth of an embryo, perhaps that would be better. The growth of an embryo will be an example of increasing complexity and organization, and the reason that it avoids degeneration, or let's say, perhaps a better example might be a tree growing from a seed, start with a tiny seed, end up with an enormous California redwood or something. Good example of a system that's going more and more complex, and it avoids degeneration by exporting the entropy it creates. In other words, every time we see self-organization occurring, we pay a price, and the price we pay is the creation of a certain amount of entropy. But if this entropy can be exported into the wider environment, then that's okay. There is no conflict with the second law of thermodynamics. So what we can conclude then is that the entropy of the universe as a whole is going up. There's no doubt about that. But that doesn't mean that at the same time we can't have this unidirectional advance of organized complexity. We can have it, but we pay a price, and the price we pay is that growth in entropy. In a little while I'll tell you about who's going to win the battle at the end. So what ingredients do we need then to get self-organization to occur? What are the key features now that we've discovered this marvelous thing called self-organization? Why weren't people writing about it 50 years ago? Well, largely because scientists were focusing on the wrong thing. They were focusing on closed equilibrium systems that were basically linear in nature. It's a technical point I don't want to get into. And they ignored processes like the dissipation of energy, except where it occurred very close to equilibrium. But it turns out that if we consider open systems that are driven maybe far from equilibrium in the way I've described, that are dissipative, that is, they're producing entropy, but exporting it, and this key mathematical quality being nonlinear, which crudely speaking means that a nonlinear system is more than the sum of its parts. A linear system can be decomposed into its component parts and put back together again without anything happening. Everything that happens to the whole is just the sum of what happens to its individual parts. In a nonlinear system, the whole is more than the sum of its parts, and it can do new and surprising things. So if you have these different properties present, then matter and energy do have this innate ability. You don't have to actually make them organize, they organize themselves. And hence Popper says that the universe is creative. I like to think of this as magic matter. That Prigogine doing his chemical experiments, or you standing in the kitchen heating the fluid from below, these humble things that one does, the matter magically has these qualities of being able to organize itself. But it's not magic at all, really. It's just ordinary physical forces, but we've overlooked this capacity for them to cause this, to bring about this self-organization. So this growth in organization or organized complexity, this optimistic arrow I've been telling you about, is it a law of nature? And I've spent a lot of time thinking about that as to whether we should really call it a law of nature. If it is a law of nature, it's not of the sort that we're very used to. It's really more a tendency, more a predisposition for matter and energy to develop along certain pathways of evolution towards more complex and organized states. And I think that the best way of expressing this is by the beautiful words of Charles Birch, whose book On Purpose so well describes many of these things. Creation is not by fiat, but by persuasion. And I think you see, we've all had this image of the laws of physics somehow reigning supreme and subjugating the material objects of the universe to conform with them, so that the planets, like in the picture I showed you at the beginning, I think epitomized this view of the universe, the old Newtonian clockwork universe in which everything had its place, and in which strict mathematical laws, eternal laws, constrained particles to move according to precise rules, and there can be no deviation from them. What we're learning in the new physics is that the universe isn't like that. It's not like a machine which is fixed in advance with its destiny already written into its component parts. It is more that the future is open, that there's an indeterminism. And we see this indeterminism coming not only from quantum physics, but also from things like the theory of chaos, and the fact that these self-organizing processes that I've been dwelling upon are not predictable in detail in advance. That you just push the system away from equilibrium and suddenly it leaps into one of these new states, and you might never have known about it unless you did it. These things are not laid down in advance, but nevertheless the general tendency from simple to complex is all the time built into these processes of nature. They are part of the general unfolding of the natural universe. And so talking about persuasion, I think, is a very good way. That this directional growth in organisation is more like persuading matter and energy, but not compelling it to develop in certain ways. It's clear that there's no compulsion, because something horrible could happen tomorrow. An asteroid could strike the Earth and wipe out all life, and obviously that would be a big setback. As far as organisation is concerned, that would be a backward step. So there's no law to say that complex organisation has got to advance, but given a chance, all things being equal, so to speak, then it will advance. So we see that it's really not so much a law in the old-fashioned sense as a tendency or predisposition. Let me say a bit more about the nature of complexity. I've been using this word complex, and I think we can all recognise in nature that there are systems which are more than just complicated. They're complex in a manner which I can best describe as being organised, or at least having fashionable way of talking about it, having holistic properties. And what I mean by that is that, again, the whole is greater than the sum of its parts, that certain physical systems have a cooperative property, that their components organize themselves together to produce a coherent whole. It might just be that great red spot, or it might be something much more interesting. And the question is, can science find some way to firm up this idea, to actually capture this elusive quality of complexity of an organized nature? And in just very recently, in very recent years, a lot of progress has been made on this, and I just want to give you a glimpse of what that progress is. Trying to distinguish between what has become known as shallow and deep complexity. Shallow complexity is just mere complication, and a good example of shallow complexity would be a gas full of molecules, like, say, the molecules of gas, of air molecules in this auditorium, that are just rushing around chaotically and bouncing into each other and not doing anything special. It's just sort of boring random mess. Okay, so that would be a random gas, and that's an example of total disorder, total chaos, anarchy, if you like. The other extreme, which is simplicity, regimented simplicity, the emblem of that will be the crystal. Crystal might be a very beautiful thing, but it's actually in many senses a very boring thing. It just consists of a lot of atoms in a lattice in a regular array, and that's it. The pattern just repeats itself endlessly. So crystal represents one extreme, boring simplicity, regimented simplicity. The random molecules of gas represent total anarchy. Neither of these really captures the essence of what is interesting and beautiful and inspiring about the universe we live in. The extraordinary thing about our world is that it's poised between these two extremes. We can imagine a universe which is just a crystal, nothing more, and we can imagine a universe which is just total chaos. Neither of these things is really terribly interesting. What we have is something which is, as I say, midway between these two, and it is something with this quality of organized complexity. Now contrast the crystal and the random gas, for example, with this thing. This is a cell from a plant. And of course, if we were to get a microscope on this and look in greater and greater detail, we see layer upon layer of organized complexity right the way down to the smallest scale of size. And the important point about this is that it is a unity, that the processes that are going on in there are all in some sense cooperating with each other towards some sort of common goal, or at least to produce a sort of unified pattern of behavior. Notice that there's more to organize complexity than just a complicated set of shapes. If we look at a fossil, we can see that has a fossil of a dinosaur or something. We can see that has a lot of complexity to it, and that it was once highly organized. But the essential thing about a living organism is that it consists of process as well as structure. And the organization that I'm talking about refers not just to how things are shaped, not just how they're structured, but how they behave. It's the behavioral complexity that's so interesting. Another example here, this is a network of nerve cells in somebody's brain. I don't happen to know whose, but you see again this intricate, elaborate network. This isn't like a random gas. This isn't a random wiring diagram. It's something of a much more highly organized nature. And the last example I want to give you is another very humble example, just a frothy fluid. Even something as simple as foam on the seashore, on closer inspection, if you look very carefully, is a very rich and elaborate structure full of highly nonlinear effects that lead to the formation of wormholes and bridges and all sorts of things. Well, I've been talking about the laws of physics and this tendency for things to become more and more complex with time. I just want to I haven't got too much longer, so I'd like to finish off by asking what class of laws can convert simple initial states into complex states? What laws of physics can actually bring this about? Can any old laws do it? What class of initial conditions, that is, if we imagine the Big Bang starting everything off, what class of initial conditions lead to this type of deep complexity of the organized form that I've been talking about? And it's my belief, although it's only a conjecture, that both the laws and the initial conditions actually need to be very special. That it's not a generic feature of any old dynamical systems. You couldn't have any old ragbag of laws and expect to do this trick, to actually get matter and energy to organize themselves. So if we think of the history of the universe as the great sausage machine, then what is actually happening, the sausage machine we can think of as the laws of physics, you see, and they're not just any old laws, they're such that when you put simple stuff in the top, like, 1 second after the Big Bang, nothing much going on, just uniform gas, you stick that in at the top, and out comes this organized complexity at the bottom. And the point is that if you go to the great cosmic engineer and buy a load of these machines at random, they're not going to, what comes out the bottom is going to be not a lot different from what goes in at the top. But if you pick the one that corresponds to the laws of physics in our universe, then what you get is like magic, because the stuff that comes out is so much more interesting than the stuff that went in. And this sort of suggests, a little bit, to many people at least, an analogy with the notion of design or with a blueprint. We're used to the idea, I mentioned embryos briefly, we're used to the idea that the embryo unfolds in some sense, it develops. Development just really means unfolding, and that it unfolds not at random, but according to some pre-existing blueprint, which is encoded in the DNA. So when we see an embryo develop, what we see are later, more organized states, which have been programmed for, so to speak, in the DNA that the embryo has inherited. And so this idea of biological complexity unfolding according to a program makes some people believe that in addition to there being a blueprint for living organisms, is there a blueprint for the universe? Is there a cosmic blueprint? And the answer is, well, yes, at least in the sense of the laws of physics, because, as I've explained, any old laws of physics won't do. It's got to be very special laws to bestow upon matter and energy this extraordinary ability to be able to leap spontaneously into new states of order and organization. So we get the central message then of this lecture, which is that in our self-organizing universe, the laws that permit a spontaneously creative nature are actually very, very special in their form. And I think this gives us something that I call teleology without teleology. Let me just say very briefly that teleology is the belief that the states of the world are dictated by end or final causes. Aristotle believed that among the variety of different causes that affect physical systems, there are those that are somehow goal-oriented, so that there exists some sort of plan or fixed idea of what the final state of the system should be, and the system is then drawn towards that state. And particularly with living organisms, we can see a lot of evidence for them having goals. It appears as if they are directed towards certain goals. But biologists don't like the idea. In fact, scientists generally don't like the idea of teleology. It's considered bad news to suppose that things are actually behaving in the way they do in some sense on purpose, or as if being drawn towards these final goals. But what we're getting here is sort of backdoor teleology, because although, as I've been at pains to explain, the particular path of development of these systems is not laid down in advance. It's not as though there exists a goal or a blueprint, say, for every human being here tonight. you're not actually written into the laws of physics at that level of detail. Nevertheless, the laws of physics are such that given those laws and given random input, nevertheless the development along the pathway of evolution towards things like living organisms and conscious organisms is something that's written into the laws of physics. And so it's as though the universe behaves as if it is the product of design, even if it has achieved its present state without any specific end goal in mind. Now, some people, of course, like to believe it is the product of design, and there's nothing I'm saying that conflicts with that, but you don't have to suppose that it's been designed, at least in all its details. And I like to suppose that there is an openness in the universe, there is a sense in which the future is not fixed in detail, that things, if you reran the movie again, things may have turned out to be very different indeed. But I think in their broad features, that is, for example, the existence of life and consciousness, the replay would be very similar to our own. So, seeing as I've raised the subject of consciousness, again, this sausage machine can do the miraculous thing that you put matter in the top, and out comes mind at the bottom, that matter organizes itself to a certain level of complexity where it becomes reflective. And that seems an amazing thing that can happen without any direct interference. And this leads to misconception number 2, which is that man is an incidental and irrelevant feature of the cosmos. Remember the quotations at the beginning, very much in the spirit, not only is the universe pointless, but that we're pointless too, and that not only we're pointless, we're just accidents that occur as a result of some random processes on some remote planet in some remote corner of the universe of no fundamental significance at all. And I think that this is a terrible way to look at our place in the universe. I think that conscious life is actually a fundamental and not an incidental feature of the universe. So in some sense, we're written into the laws of nature, as I've said. Now, that doesn't mean that individual human beings are written into the laws of nature. I don't think if you look very carefully at page 2508 of the Great Book of Nature, you'll find your name in there. However closely you examine the mathematical laws of nature, we won't find that level of detail preordained. But I believe that if we examine the laws of nature closely, we can see that, for example, the emergence of life or the emergence of consciousness is actually built in a very primitive way. I don't have time this evening to go into the details of that. I will be addressing that issue at the science breakfast tomorrow morning. I've used the word we, and I just want to caution you that it could be either of these. It doesn't have to be Homo sapiens. I do want to emphasize that I'm not saying that Homo sapiens stands at the pinnacle of some sort of evolutionary tree that leads all the way back to the Big Bang and that featureless void that it started with. It's not that the universe, that the purpose of the universe is to produce us so that we can go around giving lectures on the meaning of it all. That is not the idea at all. But neither is it the case that we're just here for the ride, that we just happen to have formed by some accident. If you reran the movie again, you probably wouldn't get I'm sure you wouldn't get Homo sapiens again. You might get the green creature on the right. It doesn't matter. What matters is that somewhere in the universe, life and consciousness would emerge, and that the universe would in some sense engineer its own awareness. And I think this couldn't be better symbolized than the famous U-shaped entity of John Archibald Wheeler, who invites us to contemplate a universe that starts out with the Big Bang here and develops, expands and develops over the eons, ever greater complexity until it leads to human observers, or any observers, who then look back at the Big Bang and reflect upon the processes that gave rise to them in the first place. And by these processes, the universe becomes self-aware. The spirit of what I've been talking about has been nicely captured by Freeman Dyson, who says that I do not feel like an alien in this universe. The more I examine the universe and study the details of its architecture, the more evidence I find that the universe, in some sense, must have known we were coming. And I really concur with that. I feel that is the essential sentiment that I've been trying to communicate, that that not necessarily we as human beings, but that we as conscious, reflective individuals do have a role, we do have a place in the universe. And to give you my own particular feelings, I'd just like to conclude by reading to you the last few words from The Mind of God, which is my next book. And I think this will make a nice little epilogue to what I've been saying this evening. There's just 2 paragraphs from the end. So the central theme that I'm exploring in the book is this, that through science, we human beings are able to grasp at least some of nature's secrets. We've cracked part of the cosmic code. Why this should be, just why Homo sapiens should carry the spark of rationality that provides the key to the universe, is a deep enigma. We, who are children of the universe, animated stardust, can nevertheless reflect on the nature of that same universe, even to the extent of glimpsing the rules on which it runs. How we have become linked into this cosmic dimension is a mystery, yet the linkage cannot be denied. What does it mean? What is man that we might be party to such a privilege? I cannot believe that our existence in this universe is a mere quirk of fate, an accident of history, an incidental blip in the great cosmic drama, because our involvement is too intimate. The physical species Homo may count for nothing, but the existence of mind in some organism on some planet in the universe is surely a fact of fundamental significance. Through conscious beings, the universe has generated self-awareness. This can be no trivial detail, no minor byproduct of mindless, purposeless forces. We are truly meant to be here. Thank you very much. Now, it's not over yet. Could I make a suggestion? First of all, if the people who operate the lights wish to turn them up a little more, I have no objection to that now. The only problem is that if I'm going to take questions here from the stage, I have to see people's hands go up. We have a period of about a little over half an hour where I can answer some questions. In my previous experience, there often are questions after dealing with topics of this sort. I believe some of you are writing them down, and if you will pass those in, I'll make some attempt to answer them. I don't guarantee every question will be answered, but most of them are answered in the book, either in the Cosmic Blueprint, on which this lecture has been based, or in The Mind of God, which is the forthcoming book, or their related titles. So first of all, those of you who feel you've had enough and would like to leave, please do so, and then when things have settled down in a moment or two, I'll take the first question. Meanwhile, Terry, do you have any written questions that I should look through?
You can go to the microphones if you want to ask a question now, and then there'll be now they'll bring some down.
You don't have any of these written ones?
Not yet.
Okay.
If somebody wants to ask a question now, you can go ahead.
Do we have a question to start with? If I stand here, I can probably see more easily for the moment. Yes, I sort of had this fear that people at the back wouldn't get a good look in, so I'm going to start by taking a question. I think there's a lady waving at me from up at the microphone there. Would you kindly go ahead and ask your question, and then I'll repeat it if we don't hear.
Yes, thank you. I have 2 questions, and you can pick one because one may be too personal. One question is, have you attempted to correlate your theories to human political systems, such as fascism versus socialism? And the other question is, what was your early conditioning by other humans as far as religion or philosophy?
Right. Can I take the second one and not the first? I don't want to get into politics if I can. I think it's very important to realize that science is done by human beings and that scientific theories are the products of the human mind. And for me, the most astonishing thing is that the human mind, because of its immersion in this cultural milieu, can nevertheless produce things that seem to have real value. And I think that there is more to science, but you see, it's an extraordinary thing. Why is it that our minds are such that we can give rise, for example, to elaborate higher mathematics, which finds such ready application to things like the structure of the atom or the internal properties of black holes. For me, it's a truly astonishing thing that in spite of the fact that, of course, we all have cultural roots, cultural conditioning and so on, nevertheless, we can, so to speak, unlock the secrets of nature. And what fascinates me is that the process we call science is actually the product of Western European culture. I think that is, it is generally considered the case that what we call science has that type of cultural background to it. Now, just why it is that Western European culture has produced science is an interesting thing to wonder about. And in many ways, I think one can trace back the thinking, the birth of science, to the fusion of Greek philosophy and the Western religions, Judaism, Islam and Christianity, all of which have the notion of a creator who orders the universe in a rational manner, and that what science does is uncover this rational plan, so to speak. So the origins of science and theology in Western Europe are very closely intertwined. That's not to denigrate other religions. I think science is a product of Western European culture, and so inevitably my conditioning has been from Western European culture and from a Christian background. Now, I'm not a religious person. I grew up in England, in London, in a community where one went to church at Christmas and Easter and weddings and funerals and so on, but didn't take it too seriously otherwise. And I think that's more or less it. People whose beliefs are sincere but fairly unsophisticated. And my own interest in these issues really began with my scientific work about the age of 18, when it seemed to me that the truly deep issues of existence, things like the origin of the universe and the existence of observers and so on, really had to be tackled by taking a scientific approach. And it was through science, and in particular through physics, that I came to deal with these things, which now, of course, have begun to trespass on the areas that were formerly just the province of religion. And I think one of the most fruitful exchanges that have taken place in recent years has been the dialogue between theologians, philosophers and scientists on these deep issues of existence, because I think we have a lot to learn from each other. And I greatly, in spite of the fact I don't really have a strongly religious background, greatly value my encounters. Just in the last few months I've met both the Pope and the Dalai Lama, and I've greatly appreciated my encounters with these great religious leaders. So does that answer your question? I hope so, because that's what we have yet. So next question. We have some written questions here.
Avoiding duplication.
Okay. Right. You be keeping an eye open for people on the floor then. So what is the role of time in self-organizing systems? Will the faster evolving systems be the one that predominates? No, fast doesn't necessarily mean better, I don't think. In both of the disorganizing and the organizing processes, the role of time, the key thing about time is that it's directionality, not its rate. The point about these things I've been talking about is, if we take a movie film and play it backwards, we would notice that there's a change. So these things have an inbuilt arrow of time, but the rate at which they proceed seems to depend upon circumstances. There is a general tendency that the pace of events in the early universe was much faster than it is now. And so if we look at the present state of the universe as being like the product of a long sequence of self-organizing processes, then most of those processes took place in the very early stages of the universe. And this is just a general property that as the universe expands and cools, things just happen more slowly. So I would say the important thing is the directionality, not the pace, but if you ask me about pace, it was faster in the past. I don't know really whether one can say that fast change causes predominance. I don't think there's any evidence for that. Now, what do we do? Terry, do we go on to the next one, or do you have a...
Is there somebody standing at the mics? And there's somebody over there.
Are the laws of physics the result of our Big Bang, or could a different set of laws have been generated with a slightly different Big Bang? Very interesting question, very much addressed in the mind of God, incidentally. there are two points of view about this. One is that the laws of physics came into existence with the Big Bang. In other words, that the universe and its laws sort of popped out of nowhere with the whole package intact. That's one point of view. The other point of view is that the laws transcend the universe. That is, that the laws have an independent existence, and for those people like myself who like to believe that the universe originated in a law-like event, that is to say that we don't need to consider the origin of the universe as a supernatural act of special creation, but something that can occur given the laws of physics, it's therefore essential for me to think of these laws as having this independent existence. Because if the laws came into existence with the Big Bang, they could never explain how the Big Bang went bang. I think that's clear, isn't it? So you have to have transcendent laws. And people who believe in these transcendent, timeless, eternal laws are sometimes called Platonists, because Plato had this idea of mathematics and perfect forms and laws, I suppose in some sense, existing in this realm out there, you know, beyond space and time, beyond the physical universe. And so people like myself who believe that these laws and mathematics that describes them has some sort of independent existence have to call themselves Platonists, and for a robust defense of Platonism and this image of laws, in addition to reading The Mind of God, you might like to read The Emperor's New Mind by Roger Penrose, who's a self-proclaimed Platonist. So that's an interesting set of questions there. Okay, on to the next one. Do the Egyptians, Mayas, know more about purpose, the purpose, than us? Evans. As a scientist, I'm bound to say that I'm impressed with science. I think it has advanced our understanding of the world enormously, and it's also advanced our understanding of our place within it. It hasn't done so much to advance our understanding of our fellow human beings, I might say. And of course, for many people, the purpose in their lives is much more bound up with their fellow humans than in their images of the cosmos as a whole. It's very easy for people like myself who spend all their time preoccupied with a sort of broad picture and worrying about when the universe is going to end and are we going to be swallowed by a black hole and all that sort of thing, to forget about the fact that really the most important things are whether your family have got enough to eat and whether they're going to get a decent education and so on, the preoccupation of so many of us. So when it comes to those sorts of things, I'm sure that the Egyptians and the Mayas were no better, no worse than we are in groping towards some meaning in their own personal lives. But when it comes to putting us in the broader picture, I do think we have the edge on them. Okay.
Why don't you take
the next? I think I'm going to have to because I can't answer.
There's one over there. Why don't you start with that?
Yeah, do you believe the human race will ever be able to achieve artificial time travel?
Sorry, can you repeat that? It's a bit,
do you think that we'll ever be able to achieve artificial time travel?
This is a very different sort of question. This is a question about time travel. I've been lecturing to some high school kids in the last day or two about this. Perhaps you're one of them. I can't see it from here. I'll deal with this one very quickly. First, let me say, which something comes as a surprise to a lot of people, that travel into the future is not only possible, it is happening now. That is to say, we can... in fact, the people up there, you see, are travelling into the future a little bit faster than the people down here, because it turns out that time runs a bit faster the further away from the Earth you get. And you can actually measure this, and a friend of mine actually has made a clock that is sufficiently sensitive that he can take it to the top of a tall building and show that it runs a little bit faster there than it does on the ground floor. These things are actually reality. By making particles move in particle accelerators very fast, you can slow up their time relative to our time by a factor of 20 or 30 or even more. So we know that travel into the future is a reality. Travel into the past is very problematical, because if you can go into the past, you get into all sorts of paradoxes which are well known to people who watch films like Back to the Future. You can go back and in an unpleasant variant of that particular film, you could go back and shoot your mother, in which case you would be in certain difficulty because if she was dead before you were born, then you wouldn't be there, you wouldn't be able to go back in time and shoot your mother, and so on. So time travel into the past leads to desperate paradoxes. Having said that, in the last 2 or 3 years, some of us have actually been quite excited about certain physical systems called wormholes, which are related to black holes, which do seem to provide a very, very slim possibility of travel into the past. And the reason we're interested in this is because I don't think any of us really believes that you can travel into the past. And so if it appears that the laws of physics as we understand them, even in the most outlandish circumstances, should permit travel into the past, it shows us that there's something wrong with those laws, and so we're still in business. So basically that's the answer to that question.
We'll take another one over here.
We'll take another one from the floor over there. Yeah.
At the beginning of your lecture, you said that you would end up by telling us where this race between disorder and organization would end up.
Oh, yes,
I can see that in contemporary terms, it's very obvious that organizing and randomizing forces are very essential to evolution. But I would be interested in your vision of the so to speak, long-term destiny of how these two factors can coexist.
The ultimate fate of the universe.
Well, what it's likely to do.
Yes, I'm sorry, I'm pleased you asked that because I had intended to tell you. Not to tell you how the universe is going to end. Oh, dear. Missed that one. I can come back to that next year. The short answer is that we don't know. Otherwise, I'd have slipped it in at the end on a transparency. But let me tell you why it is that I think we can't just accept Helmholtz's version. See, Helmholtz said it's all going to slide towards the heat death. That's the end of it. Now, in those days, they didn't know the universe was expanding. Now, the point about the expanding universe is this. Either it'll go on expanding forever, or it won't, and if it doesn't, then what will happen, it will get to some sort of maximum size, so to speak, and then it'll turn around and then it'll start to collapse. And this collapse will get faster and faster and faster until the whole thing reaches what we call the big crunch, which is like the Big Bang in reverse, where everything's scrunched together and you get total obliteration. Now, obviously, that is extremely bad news. I mean, it can't be worse than that, can it? I mean, it can't. Now, that's not the heat death. That's not Helmholtz's heat death. That's death by crushing or something, although it turns out it actually gets very hot before it finally obliterates. So if the universe weighs enough, then eventually the whole show will go off the road, and then I think that will be the ultimate triumph of the laws of disorder. However, we don't know that this is going to happen. To find out whether it's going to happen, you have to weigh the universe. No mean feat. In fact, you might feel that it's absolutely hopeless to try and weigh the universe, but it's not so, because one way in which you can do it is you can weigh the individual bits and pieces. You can weigh the Earth, for example, weigh the Sun. We know roughly how much these things weigh, and then you tot up how many there are out there, and there's a lot. And then you have to see if they're a certain number, and it's very, very curious, because it's really the number of atoms in the universe that matter. It turns out that if there are about 10 to the power 80, that's one full of 80 zeros. If there are that number of atoms in the universe, then it will collapse. And when you actually add them up, you get about 10 to the power 78. You know, awfully close, awfully close. I mean, it's sort of suspicious that maybe there's something going on here. It's designed to give us all a nervous breakdown. And to make matters worse, there are all sorts of things which aren't atoms, which also gravitate, all sorts of subatomic particles and things going through us right now that we don't feel. And when you start adding those up, it's sort of looking like 10 to the 79, maybe even 10 to the 80. And at this point, cosmologists start squabbling with each other between those that say, yes, it really is 10 to the 80, the whole lot's going to collapse, and those that say, don't worry, it'll keep on expanding forever. Now, that's the first part of the answer. If the universe keeps on expanding forever, will it degenerate into a heat death? Well, the good news is, even if it does, it won't happen for an awful long time. And I'm talking awfully long because, you see, the universe is about, 15 billion years old at the moment. We're not talking about billions of years, we're talking about trillions upon trillions of years before the reservoir of negative entropy, which is on which everything is running, is going to give up. So in other words, the organizational advance can continue for unthinkably long durations in the future. So this undue emphasis on the degeneration of the universe over the last 15 billion years, as though everything's sort of cracking up. I mean, it's quite ridiculous. We're just at the beginning of this great unfolding of things. We're at a very early stage. And if you actually want to know, if you're one of these people who are not prepared to accept trillions and trillions of years, but you want to know, supposing there's an infinite amount of time, what will happen in the end, then you start sitting down and doing calculations. And it turns out that it can go either way. It depends very much on the specific details, but there are certainly many models of the universe in which it goes on expanding forever, and there is never a point at which the total disorder triumphs. There is always scope, always room for useful energy to be manipulated and used for self-organizing processes. It may get harder and harder, but it will never become impossible. In fact, Freeman Dyson has done a rather interesting study of the ultimate fate of the universe based on these ideas, and even in a worst-case scenario, which actually needn't be anywhere near this bad, he finds that although for example, individual communities like our descendants may find it harder and harder to scrape up the energy necessary to keep going, they can nevertheless, by a process of hibernating for ever longer periods of time, still manage to do this. And the integrated time span of these descendants can actually be infinite, even though they spend longer and longer periods in the dark or doing nothing. So it may get awfully boring at the end, but it's not necessarily totally hopeless. So that's the answer to that one. So shall we take another
One from up above.
One from up above?
Oh, right.
Up there.
Yes.
In relation to the Heisenberg uncertainty principle,
Right.
you have a choice of location or momentum.
That's great. That's great.
Is number one, is that not true for any body in random motion? And number two, do you think that consciousness can in itself be considered a tool, a measuring tool for the way we look at the universe, making it sort of relative?
Okay, first question. The Heisenberg uncertainty principle certainly applies to everything, even to macroscopic bodies, but the effects of the uncertainty are so small that we don't usually worry about them. Is that what you meant?
Yeah.
Okay.
I mean, you have a choice of location or momentum, and then the experimenter in himself affects the outcome.
He's able to choose which of these two qualities to provoke, so to speak, into existence. Yes, we can. In case people don't know about this, it's usually discussed in connection, say, with individual atoms or electrons. Imagine we have an electron. Because of the Heisenberg uncertainty principle, we can't say in general that it is both at a definite location and has a definite motion. But the experimenter is free to choose to measure, say, the location, in which case what you get is an electron at a position, or measure the momentum, in which case what you get is an electron with a momentum, but you can't have both. And it is up to the experimenter which of these two aspects of the reality of the electron shall be manifested. And so the observer or the measurer has a hand in creating or provoking the nature of the reality that shall be. And that certainly does apply to all objects, as far as we know, but it's only important and significant, I think, at the atomic level.
Do you think consciousness can be used as a measuring tool?
I don't quite know what you mean as a measuring tool.
I mean, the way we perceive the universe is because we have the ability, the way we are, to look at it that way.
Right.
And it might exist some other way if someone had another way to look at it.
Right. First thing I should say is it's been quite clear from the lecture I've given that I take consciousness seriously, and I don't consider it a trivial addition to the universe, just some little quirk of evolution that may or may not have arisen. I think it is an absolutely fundamental aspect of nature, for reasons that I want to elaborate more in my address tomorrow morning. That's the first point. The second point is that inevitably, in doing science or doing any sort of observation of the world, we do this through the medium of our own consciousness. So, in a sense, it is the fountainhead of all measurement and observation. When we use tools, when you mentioned the word tools, we use scientific instruments to make measurements, but it's only when we can relate measurements to give meaning to those measurements, relate it back to our own theories. We have to provide a theoretical structure before we can understand it. So in that sense, consciousness is part of, absolutely, part of all measuring processes, but most especially in quantum mechanics, as I've already discussed, where it intrudes in a much more basic way than it does in ordinary physics. Yeah. I've got here what is free will. That's a big issue. Must I answer that one? Some people think free will is just an illusion or it's just a feeling. I often like to say to people, what difference does it make whether you are free so long as you feel free? Because if you feel free, then that's good enough, isn't it? The problem about trying to define free will is that you rapidly go round and round in circles. Some people would like to say free will means that if you could rerun the universe again in every detail except that one point of decision, that it would somehow bifurcate and you get a different outcome. Well, you can't do that experiment, so it's a rather useless definition of free will, I think. I think that the way I like to put it, and in fact, one book that I didn't mention explicitly, but which is also just about to appear, called The Matter Myth. I have two books about to appear simultaneously, The Matter Myth and The Mind of God. The Matter Myth is really a celebration of post-Newtonian thinking, a celebration of post-mechanistic and post-materialistic thought. And the last words of The Matter Myth, which I remember, without having to read them out, I can tell you, it has to do with the fact that the philosopher Gilbert Ryle coined this term, the ghost in the machine. Biologists like to regard our bodies and our brains as just machines, and then some people would like to feel that we have this mind or soul or free will that somehow infuses the machine and takes over a bit like the driver taking over the controls of a car, and this Gilbert Ryle somewhat cynically called the ghost in the machine. And a couple of generations of philosophers and psychologists have been doing their best to exorcise that ghost from the machine because they don't like the idea of ghosts in machines. And I agree with them. I think that there is no ghost in the machine, not because there's no ghost, but because there's no machine. And the point about that is that we don't live in a universe which is just a mechanism. It's not just a clockwork. Because of what I've been telling you today, it is something which is open. The future is indeterminate. It's not fixed in advance. The general tendencies are there, but the details are not fixed in advance. So the way I like to think of it is not so much do human beings have free will, but to see that this freedom to choose pathways of evolution, pathways of development, exists not just for human beings, but in the wider world as well. Even the stupid world of the world of stupid molecules like water molecules. There's a sense in which they have some sort of freedom. So I understand free will to really mean this openness, this fact that the future states are not already fixed in advance, and that we can participate ourselves in bringing about these future states. But it's something that's not just limited to human beings. It's a property of nature. Of course, it's focused and concentrated, and we're aware of it in our role as human beings, but it's actually a broader phenomenon. So that's my own personal point of view. It's very much a personal view, that one.
Do share three.
Okay, who wins? Complex organizational entropy. Okay, that's that one I've dealt with. How many people worldwide are engaged in the serious pursuit of cosmology? Okay. Well, let me think. 8, I think. It's like all these things, it's difficult to know where to draw the boundaries. If you ask how many people would describe themselves on their tax return as a cosmologist, it can't be more than a handful. I mean, we are talking almost single figures. If you say how many people have some input into the great enterprise of cosmology, then you've got all the astronomers and you've got the physicists who like to theorize. You've got all the particle physicists who like to feel that they're simulating the conditions of the Big Bang, and various theoreticians and so on. And then you're talking hundreds or maybe even thousands of people who have some sort of input into cosmology. Very few people would actually describe themselves specifically as cosmologists. I think I probably know all of them, actually, and it's not that many. I usually describe myself that way, I must admit, to say I'm a cosmologist rather than a theoretical physicist. These days you say I'm a theoretical physicist who specializes in cosmology. So these descriptions are difficult to pin down. There's a supplementary question: what would be the universal temperature of the universe if the heat death were achieved? That's a very good point. What is more interesting is I wonder what Helmholtz would have answered that, because in those days it wasn't terribly clear what the large-scale structure of the universe was, whether it was infinite or whether the stars were aggregated together in a blob and then it was empty space outside. In the latter case, the equilibrium temperature would be 0 because all the heat would escape off to infinity. But if the material were distributed everywhere on average uniformly, then you could work out what the temperature would have been, and it would be awfully low because the point is that there's so much empty space between the stars that when you spread all the heat energy from the stars around in that empty space, it's very, very low indeed. But in fact, we now know that the universe is expanding, so whatever temperature it's settled down to, as the universe expands, so the temperature falls. So there's a very simple law. When the universe doubles in size, take some particular volume of the universe, when that doubles in size, the temperature halves in value, and it'll just go on sliding down. The average temperature of the universe now is only about 3 degrees above absolute zero. So it's minus 270 degrees centigrade. So that's it's already pretty cold. Although having said that, there's still a lot of heat energy there. Although the temperature's low, there's so much of this heat energy. There's quite a bit of it. But that will just go on. If the universe goes on expanding, that will just tend towards zero. Now, do we take another question from the floor, Terry? What do you think?
Let's do one more.
All right, one more, please. How is it possible to get something from nothing? That's another lecture. That's the lecture that Stephen Hawking's going to give. And basically, quantum physics tells you can get something from nothing. Let me just give you, I'm not going to get into the issue of the universe coming from nothing because it would take too long to do all the details of that, but just to give you a sort of flavor for what I mean, that in the laboratory, if you examine processes at the subatomic level, you often find that particles can, so to speak, just pop into existence out of nowhere for no apparent reason, and sometimes just disappear again for no apparent reason. You're always getting something from nothing at the atomic level, and it's actually an observable thing. So when quantum physics came along, I suppose about in the 20s, late 20s, early 30s, it became obvious to physicists that you could have something from nothing, and it's connected with this Heisenberg uncertainty principle. It tells you that at least on a small scale of size, things can just come out of nowhere for no reason. That there isn't a rigid determinism of things. The supplementary question again, can you explain black matter? If this refers to dark matter, I mentioned this a moment ago, this question that when we try to find out how much matter there is in the universe, basically to weigh the universe, we have to take into account the fact that there's a lot of unseen or dark material, and there are about 32 different things, I think, at the latest count that it could be. I'll give you a few for instances. Could be black holes, could be neutrinos, could be gravitational waves, could be exotic particles that carry names like photinos and gravitinos, and generally speaking are known as cosminos or cosmions. There could be a huge variety of different types of particles which we don't see because they don't interact very much with ordinary matter. They just go straight through. And it's a sobering thought. I once calculated that every time you glance at the sun, more neutrinos from the sun pass through the pupil of your eye than there are people on the Earth every second. That is the case. So there's this huge number of particles that we just don't feel go straight through us and straight through the Earth and out the other side. So the dark matter of the universe could be one of this whole variety of different things. Now, how are we doing?
Why don't we go over here then? Yeah?
Right, a question from over here.
I have two questions. One is very similar to the one that was asked up above, but I wanted to rephrase it. If you feel like you've already answered it, then I can go to the second one. You talked about dynamic systems and how things like water form structures which you wouldn't have predicted in advance.
Right.
But maybe in retrospect, you can try to understand
right.
that.
That's
I'm interested when he mentioned the uncertainty principle, but also with evolution, which has a certain dynamic flow to it.
Right.
When people achieve consciousness, suddenly evolution is interrupted because the consciousness allows you the ability to interrupt your flow. We may all blow ourselves up, in which case that's been counterproductive. And the same way with the study of your dynamic systems, when you reach consciousness, do the laws still affect you the same way that they did when you were dumb or stupid, as you were describing before? Suddenly we're out of the realm of having things beyond our control, in a sense.
Right.
Where does that leave us for future development?
Right. I think that's a very relevant point, and I keep changing my mind on this one because Because it's certainly the case that now we are aware of what is going on and understand something of the principles of nature. We're able to, for example, interrupt the processes of biological evolution. We can engineer organisms and so on. And it's clear that, in some sense, we're not slaves to these laws or to this tendency that I've been talking about. But having said that, I continue to be struck by ways in which, when human beings, we have to think what is the next level. And the next level is not an individual human, but it's a community. And just as we, with this hierarchy of levels of description that I've been talking about, that you get higher and higher organizational levels, there is a higher organizational level than individuals, and just as a single ant in an ant colony is, I don't know if ants have free will actually, but seems to have a certain limited repertoire of individual activity, but is embedded in the purposes, whatever they might be, of the colony as a whole. So society shapes the behavior of individuals, and individuals collectively make the society, and this has its own internal dynamics. And you might think, well, but if we can figure it out, we can interrupt it or manipulate it. And of course Karl Marx had precisely this idea 100 years ago. I mean, very perceptive that, that there might be a social dynamics that one could actually manipulate. Well, I don't know what more to say about it, except for the fact that from time to time I am struck by the way, although we are apparently in control of our destiny, or we think we are, nevertheless human beings collectively do seem to behave in a way where the collective has a will of its own. That society has a sort of will that in some sense overrides the will of individuals. And let me just give you what I think is a classic example. And that is I've mentioned Marxism, that's one system. The other system is capitalism. And in capitalism we see how apparently free individuals that enter the marketplace and make purchases and so on can nevertheless give rise to processes of self-organization. And we've seen in recent years increasing interest for the application of dynamical systems, a theory in which chaos is applied to the money markets. And for example, after the 1987 stock market crash, a lot of people felt this was a manifestation of chaos as a non-linear system. Well, as I've explained, I just wrote an article on this, which is why I feel so passionately. As I explained, there's an intimate association between chaos and self-organization. And I think just as we can maybe see chaotic behavior in the financial sector, so we can see self-organizing behavior. See, people used to suppose that politicians ran the economy. They supposed that they made decisions like changing interest rates and fixing exchange rates. It's increasingly obvious that the politicians don't really know what they're doing. that they're actually just they're reacting to events. The system really has got a life of its own. The global economy is, so to speak, running itself. And it is a self-organizing system, and the individuals who think that they're free to enter into financial arrangements, in fact, are carried along by the tide of events, a little bit like the little blobs of fluid are carried into the great red spot of Jupiter. Each individual one doesn't know where it's going, it's unpredictable, it thinks it has a sense of free will, but there is a coherence about the collective system as a whole. And so I think this opens up, an enormous number of interesting questions about the next level of organization. And then you start worrying about, well, will it be computers, and will the computers take over and so on? But I think I better stop there.
Once you got it, let's take one from over here.
It's been a long time since I've taken a physics class, so I may be remembering this incorrectly, but...
Don't worry, I'll soon correct you.
I seem to remember that a self-organizing system, say take an embryo that's developing, and one that entropy is not increasing in, had to be a closed system, and yet you're saying it needs to be an open system.
It's essential that it's an open system. The second law of thermodynamics is a law. I hope I haven't given the impression that it is somehow evaded or contradicted in these processes. It certainly is the case that if you look at the system as a whole, the total entropy rises. The reason that certain systems can apparently go the wrong way is because they are open systems, and they can export entropy into their wider environment to, as it were, pay for their organizational advance. And this is particularly true in biological systems. It's very clear that biological systems are open systems, because if you shut them up in a box for long enough, then they die. Okay.
I think we ought to leave it at that. I just say that I think we're very lucky that one of those handful of cosmologists in the world has such a commitment to communicating what's going on to those of us who don't want to delve through the differential equations. Let's say thank you to Dr. Davies.
Thank you.